Hi students, it's Miss Vernon, and today I'm here to teach on section A1, radicals and rational exponents. Today we'll be focusing on three different objectives. The first being, can you simplify radicals and apply properties of exponents? Can you manipulate radicals and apply basic operations? And can you convert between a rational exponent and the radical form? Remember, as we go through the video, it's important to pause, take notes, and ask questions after if you are not understanding. Let's get started with some reviewing of vocabulary. So a radical is any term that has this radical symbol, and whatever numbers inside of the radical or the check mark part is considered to be an index number or a root. Whatever term is under the radical is called a radicand. With radicals, we sometimes will have it in radical format, or we'll convert it to a rational exponent. A rational exponent is simply an exponent that has a fraction as it that is a fraction. With a rational exponent, you'll see some similarities, but one of the biggest things to remember is when you have a fractional or rational exponent, whatever number is on the bottom of the fraction is the index number of the radical. Whatever number's on top of the fraction is simply the squaring, or in this case, of the term. And you can put that exponent on the inside attached to the radicand, or you can put it on the outside of the radical. This allows for more flexibility when simplifying or evaluating these types of problems. I encourage you to be very flexible as you learn to do this. Let's practice some simplifying. So if I'm going to simplify a radical to get an exact answer, I am going to be looking at, can I break it down or find its perfect squares, or whatever it needs to be. In all four of these examples, notice there was no number inside of the radical, so we assume that that is a 2, or we read this as the square root. So the square root of 36, most of you will very quickly tell me that that is 6. 6 times 6 is 36. When you're evaluating or simplifying a radical, you are looking for perfect squares that can be broken down or taken out from being under the radical. On the next problem, some of you might quickly say, well, the square root of 4 is 2, so this is negative 2. That is a false answer. You cannot take an even root or an even index number of a negative radicand. The reason being is, in this example, there are no two numbers that are the same that multiply to give you a negative number. Two negative numbers multiply to a positive. Therefore, this is a non-real solution, or no real answer can be found. If you were to type this into your calculator, that is what it would say. It would give you an error message. When this is an even index number, you cannot have a negative number under as the radicand. No real answer will be able to be found. Let's move on to the next problem. In the next problem, we have the square root of 50. Whenever possible, I encourage my students to look for perfect squares. In this case, I know that 25 is a perfect square, and I know that 2 times 25 is 50. If you didn't know that, you could take your calculator and say 50 divided by different perfect squares. So 50 divided by 4, 50 divided by 9, 50 divided by 16, until you got a perfect square to go in or show that it was divisible. Now you can say, well, the square root of 25 is 5, and the square root of 2 I can't break down. So this radical simplifies to 5 times the square root of 2. Let's look at the last example. In this example, we have 48. Now, Some students do not see perfect squares in 48, so they tend to do a prime factorization. A prime factorization can be referred to as a factor tree. So students might start to do a factor tree and see that they get some perfect squares that come out. So they might write this as 4 times 4 times 3. And instead of writing x to the third, they may write it out as x times x times x. Now, when you have an index number, it tells you the size of your groupings if you're dealing with variables. So I would need an x squared or 2x's in order to put that term outside of the radical. I also know that the square root of 4 is 2. So I'd have 2 times x, and the 3 and the x did not pair up. I would write my answer as 4x times the square root of 3x. Now there's one more detail we are going to add in here. Because we were dealing with an even index number, we need to tell the state that the answer is positive. Absolute value bars around this variable indicate that that x value, which could be any number, has to be positive. Otherwise, I would have had a negative and it would not have been able to come out or be taken out. Remember, we can't take out a negative when we have an even index number. If this shows up on your homework, just be patient, keep practicing, and ask lots of questions. Again, the reason we had to put the absolute value bars around it is because the index number is even, and we have to ensure that the variable is positive. Let's move on to problems that do not have an invisible 2 or that are not an index number of 2. Here we have 2 new examples. We have a cubed root. When working with a cubed root, you are looking for perfect cubes or groups of 3 of the same number multiplying together to equal the index number. When you have an odd index number, you can take out a negative value because 3 negative numbers multiply together to equal a negative. In this case, the cubed root of -5 times -5 times -5, or -125, is -5. Notice that because I had an index number of 3, it meant I needed 3 of the same number in order to simplify the radical. Pause the video and give the next problem a try. When I worked with the next problem, I started to look for perfect cubes. Now, the first perfect cube that worked out for me was 8. 8, or the cubed root of 8, is 2. And I learned that 8 times 8 times 3 equaled 192. I also recognize that I would need 3 x's in order for that to be removed out of this particular scenario. So what I did next was I took the cubed root of 8, the cubed root of 8, and I took out one group of 3 x's. When I did this, I had 2 times 2 times x times the cubed root of 3x. Notice that the 3 and the x did not group up and could not be taken out from under the radical. Finishing simplifying, I would state my final answer was 4x times the cubed root of 3x. Notice that in this problem, I don't have to put the absolute value bars around the x because we know that a cubed or odd index number can produce a negative answer out. It is only when the index number is even that I need to insert those absolute value bars. Let's move on to the next part. I have another one for you to try. Notice that the index number in this problem is a 4. So you will be looking for a perfect fourth or a term to the fourth power to remove it or put it outside of the radical. All right, let's take a look at the answer. So as I look at this, I am looking for groups of 4. 4 is 2 squared, and really that's as low as it goes, so I can't do much with that. I would need an x to the 4th, and because it's x to the 5th under the problem, I'm just going to separate it as I have 4 x's coming out, and I have 1 x left over, and y to the 8th, I can break that into 2 parts as y to the 4th, y to the 4th. Now I'm going to highlight the terms that I can bring out of the radical. Remember, the exchange rate to pull this out of this radical is I needed 4 of the same term. So when I bring these highlighted terms out, I am not going to keep the exponent of 4 because that was the exchange rate to get out. So I have x times y, and still left under the radical, I will have 4x. Now I'm going to write my final answer. I have the absolute value of x. I have y squared, and I have the 4th root of 4x. Now, some of you might say, well, Miss Vernon, why did you not put absolute value bars around the y? I didn't need the absolute value bars here because squaring something makes it positive. Because it came out as a perfect square, I don't need the absolute value bars. It would be redundant to put it there. I do need the absolute value bars around the x because it was an even index number, and I needed to ensure that that variable was going to be positive. Let's move on to talk about some other rules related to radicals. Another rule that you should be aware of is when adding or subtracting radicals, if the radical part itself is exactly the same, I can add the numbers in front of it and have a simplified answer. In this case, 5 plus 2 is 7. And notice that the radical part just stayed there. The same rule applies when working with subtraction. Notice that we have the 5th root of n and the 5th root of n. I am then going to subtract the numbers that were in front of it. It's kind of like combining like terms. When I do this, I get a final answer of 4 times the 5th root of n. Note that sometimes you will have to simplify the radicals here in order to catch that they will simplify down nicely. Another rule related to radicals is that I can take and break a radical up and take, for example, the square root of 4 times the square root of x to the 3rd, or I could write it back all as a single radical. I'm going to continue to show you that I simplified this by saying the square root of 4 is 2, and the square root of x to the 3rd is x times the square root of x. Notice I added the absolute value bars in because our index number was an even index. The same process will apply when dealing with a fraction. If I have a fraction and taking the square root of that fraction looks really difficult, I can take the square root of the top of the fraction and the bottom of the fraction separately. These two rules kind of go together and apply to the properties of exponents that we learned earlier. Now I can quickly take the square root of 25 and the square root of 36 and get a final answer here of 5/6. The last rule I have is when I have two radicals, I can take those radicals and multiply the index numbers and get a more simplified radical. This is really a fancy way of saying it's power to a power. So I have the fourth root of x, and rewriting this as a rational exponent, I would have 1/3. Then if I rewrite that as a rational exponent, the fourth root of x, I have 1/4 to the 1/3 power. Exponents said multiply those together, and that's where you get your 1/112. This is the same thing as the 12th root of x. Again, radicals and exponents have a lot in common. You'll see a lot of similarities in their properties. Let's just pause for a second and review converting between the two. This was the example from the beginning, 7 to the power of 2/5. The power of 2/5 is called a rational exponent. I can rewrite that rational exponent as a radical by putting the 5 or denominator of the fraction as the index number and the 2 or the exponent part as the power. Notice that I have the flexibility to put it in either spot. Pause the video and try to rewrite the next two. The first one will be rewritten into radical form and the second one into a rational exponent form. In the first one, you note that you will not be distributing anything. The squared stays on top of the x plus 3, and inside of my radical, my index number becomes a 3. On the second one, recall that if there isn't an index number, we assume it's a 2. So this can be rewritten as x to the 5/2. Great job. I have one last example for us today, and that is simplifying a problem like this. Notice that right now the radicals do not match, but I can see some perfect squares, so I'm going to simplify this. For example, 45 is 9 times 5. And 320 is 64 times 5. If you didn't know that one, don't worry, grab your calculator. Next, I know that the square root of 9 is 3. So the beginning one becomes 3 times the square root of 5. I know that the square root of 64 is 8. And I still have the 5 that did not pair up. Notice that they both have the same radical part, square root of 5. What this means is I can now subtract the 3 and the 8 and get a final answer of -5 times the square root of 5. You're ready to start the practice. I hope the video made sense, and if you have any questions, feel free to reach out. Have a great day.